Let's now take a look at an example and get some practice using those IV equations. So what we want to do is we want to determine the current in an enhancement mode in-channel MOSFET. Well, that's pretty convenient because that's what we've looked at so far. And so we're told that this MOSFET has various parameters. So we're given a threshold voltage, VTN equals 0.4 volts. So again, that's confirming that it's enhancement mode. We have to apply some gate voltage to create that inversion layer and turn on the device. We have our width is 20 micrometers. We have our length is 0.8 micrometers. And so typically that's the case that our length is going to be shorter. Recall micrometers is 10 to the minus 6 meters. We have our electron mobility in the inversion layer is 650 centimeters squared per volt second. Our oxide thickness is 200 angstroms. And so let me pause for a second and say you might not have seen this unit before or in a while, but the A with the little circle on the top is angstroms. And so our angstroms is going to be 10 times 10 to the minus 10th meters. So angstrom, which is 10 to the minus 10 meters. And so oftentimes we'll refer to these oxide thicknesses in either angstroms or nanometers. So that'd be a 20 nanometer oxide thickness, for instance. And then finally, we have a relative permittivity of our oxide, which is 3.9. And so I should say dielectric just to be more general. But in this case, it turns out that is the value for silicon dioxide, which is a common dielectric, at least for our somewhat large compared to our cutting edge technology devices. So we're told for this particular MOSFET, we have a VDS of 1.5 volts, and we want to find the current ID for two different gate voltages. So first we have VGS equals 0.8 volts. Second, we have VGS equals 1.6 volts. And sort of implied here is that our source is connected to ground. Okay, so the first thing that we want to do is determine what operating mode we're in. And so we can do that by considering for each of these gate voltages what our VDS SAT is. So in this case, our VDS SAT is VGS, which is 0.8, minus our VTN, which is 0.4. And we see that our VDS SAT is going to be 0.4 volts for this first case. And because our 1.5 is above that, we know that we're in the saturation region. So similarly here, we can say what's our VDS SAT. So remember, it's going to change because we've changed that VGS value. So now we have 1.6 minus 0.4, which is 1.2 volts. Our 1.5 is still above that. So we can say for both regions, we're going to be in saturation. Or both, let's say both VGS values are going to result in saturation mode for our given VDS. Okay, so what we're doing then is we're going to our equation that had Kn times the quantity of VGS minus VTN squared. So let's next look at calculating that conduction parameter K sub n. So this is our capital K sub n. And so we had quite a few things going on in that equation. And so one thing to point out is we want to be very careful with our units. So up here we see we had various length units. We had micrometers, we had centimeters, we had angstroms. And so we want to be careful that all of those are consistent such that our lengths are ultimately going to be canceling out. And so typically what we'll do is we'll take everything to centimeters. That's not necessarily required. If you're more comfortable, you can take everything to meters, but typically everything's going to be taken to centimeters. So we had our width in the numerator, so the 20 micrometers is going to be 10 to the minus 6 meters or 10 to the minus 4 centimeters. So 20 times 10 to the minus 4 centimeters times our electron mobility in the inversion layer. And so that one we're not going to have to adjust. So that's 650 centimeters squared per volt second. We then have our permittivity of the material, which we said was, and so this is part of our Cox prime. So our permittivity is the relative permittivity, which is 3.9, and that's dimensionless, times our permittivity of free space, which is 8.854 times 10 to the minus 14th farads per centimeter. So again, that value there is our epsilon naught, our permittivity of free space. And so in physics or other classes, you might have seen a slightly different value of to the minus 12th, and that's because in physics, typically that's just going to be meters as opposed to centimeters. Okay, so that's pretty much good for our numerator. In our denominator, we had a 2, And then we had our length, which again, we want to take that micrometers to centimeters. So we're going to do 0.8 times 10 to the minus 4. And that's going to give us centimeters. And then finally, our 200 angstroms for our oxide thickness is going to be 200 times 10 to the minus 10th meters. But we're going to back that off and go 200 times 10 to the minus 8th to take it to centimeters. So now what we see is the centimeters are going to be canceling out. So we'll have centimeters squared canceling there, and our 2 centimeters in the numerator canceling out. And the units are going to work out such that our overall units are going to be amps per volt squared. And so if anybody has questions or wants to see details on how to get that from our farads per volt second, just let me know. If we plug all that in, we should get a value of approximately 1.40 times 10 to the minus 3rd amps per volt squared. All right, so let's now go plug into our equation for current in the saturation region. So we had, again, our 2 gate voltages. So let's start with part A. We were looking at a gate voltage of 0.8 volts. So we have that our ID is going to be approximately equal to that Kn value of 1.40 times 10 to the minus 3rd amps per volt squared times we have our 0.8, which is our VGS, and that's volts, minus our threshold voltage, 0.4 volts, and that quantity squared. And so you can see from our units, from over here, we're going to have a volt squared, which is going to cancel out with this volt squared, and we're going to be left with just amps, as we would expect for a current. And so if we plug that in and sort of change it to a more readable format, it turns out in this case, milliamps is a little easier to interpret just at a glance. So that ends up being 0.224 milliamps. So that would be our answer for part A. So now for part B, it's the same equation. We've just adjusted our VGS. So we still have the Kn as 1.40 times 10 to the minus 3rd amps per volt squared. Now our VGS is 1.6 minus that VTN of 0.4. We're still squaring that. And as we would expect, we see that this current is increasing to 2.02 milliamps. And so that would be how we solved that example.